Hi everybody, my name is Thomas. I work on runtime is my, let's say, specialty. So OpenMP, SQL, Level 0, OpenCL, CUDA if I'm forced to. And I developed also with the help of many people. Uh, we develop also a lightweight tracer. So you will see it's a little similar to what was presented before and what we'll present in the future, but maybe a more lightweight easy to use tool just to get you started. I think we have a lot of people from the team, or by a lot of people, I mean Nathan, on the chat if he's here. So don't hesitate to just post stuff on the chat or even just interrupt me. I don't know if you can unmute yourself, but if you can, don't hesitate. Feel free to do that. So I will start maybe before with a rant. I think is important, just why you should profile. I think maybe sometime we forgot that and we have more user maybe coming from different community and maybe it's not clear to them. So I will start with a bit of ranting just because it is my talk and yes, it's nice. She did a new show, she let me do that. And then we'll go over the tools and show you some example. And I have also maybe, if we have time, depending on how it goes, from live demo on, I don't know if you realize, but Aurora is down. So on some other PVC nodes that we have, like Colin did on Chiata with a few PVC systems just to show you started. And yeah, I think this one should be conversational, whatever. Just don't please put some question and stuff like that. I think it is the advantage of this live thing is like we can interact together because if not, you can just watch the video. So please don't hesitate to interrupt me. And it's nice. So I have the feeling I'm not talking alone. So it's always good when you have people, interacting with you. So just maybe if you just need to remember one slide, I think it's easy when you have or access to Aurora, you just modulo THAPI. THAPI is the name of our overarching program. And then you just do Iprof with our profiler. It is the name of our profiler. So you do just Iprof a.out. For the people here who are very good in MPI, you can see a difference between us and MAP, who was shown before. We do MPI run Iprof, when for map you were doing map MPI run. So I'd let you imagine the difference in behavior between the two and how it is implemented. Just a little teaser if you are interested by these kind of things. So super easy. I think our goal with Iprof is really to make it super easy. It's like the nice NVProf between before NVIDIA did a lot of option and everything, and now I'm not smart enough to use it anymore. So already super simple. We have maybe, I will show you only 3 arguments, and that's it in series. This is the only thing you need to get you started in your performance analysis. And we have a few repos. So here it's the main repo, if you just want to install it from source or see the source code. THAPI SPAC with our SPAC package if you want to be able to do SPAC install. And here it is the doc, the badly written doc that I put on the official Aurora website that you can just go if you want to have more info. Okay, so now a little rant. So what we do in HPC, right, is in theory, we should remove the bottleneck of your code, right? This is what we do. This is why we are here. Your code is always limited by something, and it is an infinite amount of work to make it faster. And how we do that is just we find the bottlenecks and we work to remove the bottleneck. And then we iterate over and over again until our grant is out or the new fashion go into and we need to move project, right? This is what we do as a day job as an HPC people. It seems obvious to say, but you need to know your bottleneck, right? You need to know if something is really important. If you run on our machines, that means you should know what is your bottleneck. Is this your communication? If it is MPI, 1CCL, whatever you are using, libfabric, if you are this kind of people who want to bypass everything, or is this is the GPUs and you are using the GPU, or if it is a Python interpreter or something like that, as we showed before with all the other presentation, it is a key. It is something you should know. If you don't know, it's really bad. I think you are at least for the HPC side really missing something. My other controversial point is like Optis GPU kernel is fun, lot of presentation, lot of demo, lot of things. It's really cool, nice, you feel good. It's more or less useless personally, I think. We do HPC, we do scaling. If you are running on your machine, you should use a lot of node. If you optimize 20%, you speed up one kernel by 20%, and this kernel is used 10% of your code. Okay, good. Yeah, it's nice. It's make a nice slide, and you can maybe make a paper. It's totally useless. Just ask for 20 more on node. You have lot of node, lot of hour. It's not a good time for you to try to optimize GPU kernel. It's maybe the most obvious because it's easy to microbench, it's easy to write a reproducer, it feels good, but it's more or less useless. Most of the time, what you should really focus on is scaling, right? It is really what we should do. As an HPC system, if we are not scaling, maybe you should not run on our machine, you should run on your lab, on the cloud, I don't know where, but if you are running on HPC center, we are really focused on scaling. You have multiple ways of scaling, workflow and this kind of thing, but at least it is just your key consideration should be about scaling. And maybe now this is a question who is also maybe how can I say, not a misconception, but you should have a performance model of your code, right? Your code is not a black box. Your code, you should understand it, and you should have a have a performance model. You should know if your code is slow or is fast, right? You should just not say, I don't know, it's running, at least it's good, whatever. It slow fast doesn't mean anything, right? You should know stuff. We do science, we do real science on a machine who have like theoretical bandwidth, who have achievable bandwidth. For example, you should know how many data transfer are you doing in your model and your application, right? It is something given. You wrote the application. You should know this kind of thing. So you should know how many data transfer. You should know the bandwidth of the machine, of the NIC, of the, the card or whatever. You know how many bytes, you know the theoretical bandwidth, then you measure how much you are taking the time to do that. And then you can compare your estimation of your time to the time it actually takes, and you can see if you have a mismatch. And if you have a mismatch, it's either you found a bug somewhere or you have something wrong in your theory or whatever. But you should know this kind of thing, right? You cannot arrive and say this is slow. Slow means nothing. Slow is relative to some potential hardware. And you need to do this kind of an analysis, right? It should make sense. If you profile your code as we will do, and the profiler say you are transferring 20,000 terabytes of data, you should be able to tell me if 20 terabytes is what you expect, or for your model is totally wrong and I do far too much spurious data transfer, right? What I like personally in computer science, in HPC, is like nothing is magic, right? We are building ourselves those machines. It's not like physics where we have no control of physics, quantum chemistry, quantum physics is totally, magic. Nobody really understands this thing. You don't know. You have chaos and randomness. Not in HPC. In HPC, we should, in science, computer science, we understand everything. We build this thing, right? It's just 0 and 1 on the silicon that we, as a human, construct. So nothing is magic. You should be able to understand everything. At some point, obviously, you need to stop, but at least you should know. You should have a performance model. You should know how fast your code should run if everything go well, right? Yeah, and what I say is this one is independent of your programming model. If you are using Python, if you are using PyTorch, if you are using SQL, Cocos, OpenMP, whatever, it doesn't matter. This one is really an abstract concept, the performance model of your code. You should know. If you are, maybe I say it again, but if you are here, if you want to run on Aurora, you get our on Aurora, you should know how to scale, you want to scale. If not, you should care about performance. If you think performance it doesn't matter, I think you are not in the correct place. We are already doing HPC, And we are really here to take advantage of the machine and to be able to fully utilize the machine, right? And yeah, and performance is relative to our current hardware, relative to your model, relative to all these kind of things. So it is something really important. So I hammer down, profiling is not something nice that you should do, if you have time and if you have some freedom. It is something fundamental of the work we are doing. We are doing here. HPC, we should use the full machine. We should scale somewhere, right? It is our key point of running on this kind of system. And it is fun also. I mean, always nice to optimize and to run as we should be running. End of my rant. We can go back to now the explanation of the tools. Now that you are convinced that you should use a tool. I don't really push for any tool. We develop Iprof from historical reason because when we started with Intel, Intel didn't have on PVC any kind of profiler, so this is how we started. It's for us. We'll show some tooling for us. But any kind of profiler will work. I have absolutely no feeling about it. I think different have a trade-off, a lot of different trade-off. We can discuss the trade-off. But you should profile is mandatory, right? It is really something you should do. You should know your code. So Iprof is a tracer, so we trace API call. I will discuss that more later. And one last slide is what kind of thing we want to understand. And I think, for example, Colin in previously in OpenMP, yeah, in OpenMP, for example, give you nice use cases. I will put mine that are real life stuff that we did during the lifetime of Aurora. And it sounds trivial to say, but when you find bugs, it's far easier to fix bugs if you understand bugs. Or to be able to find bugs, you need to understand first your code so you can see something mismatch. And for example, is PCIe, it's a bidirectional data transfer. We'll discuss more about PCIe later, but that means you can do transfer in one direction, for example, from the host to the device at the same time where you can do device to host, right? It's what we call a bidirectional data transfer. If you are done doing that, you are wasting 2x of the bandwidth. And the question is like, I am doing that, and if I am not doing that, why? Or, for example, why my OpenMP map that I put here was taking 10 minutes. We saw a bug previously in the lifetime of Aurora that it was a problem. Or why SQL in order takes so much time. Or all this kind of thing. Or as we say, high-level questions that you need to know the answer. If I am GPU bound, MPI bound, data transfer bound, what is my maximum memory footprint? Can I grow more my system, right? Because I'm using only 20 gigs. Or, oh no, I am at the limit. I'm using 1 TB of GPU memory. So now I should do the opposite, try to lower my memory to run bigger system. Or what is my scaling? If I scale more 2 nodes, it's okay. And then now I run 1,000 nodes. Now I spend my time on MPI. So you should know these kind of things. So this is a question we want to answer. So what is our approach in THAPI, in Iprof, is to be kind of lightweight and to not trace everything. We are tracing heterogeneous APIs. This is what we mean by THAPI. So THAPI is the name of the project. So that means we trace library call. So we trace really the library accelerators that we are using. For example, for Aurora, we are tracing level 0 with their CUDA driver. Intel CUDA driver, we trace MPI, so you know MPI. We have OpenMP callbacks, so you can know what you are doing OpenMP, and you are working on ITT and other stuff, libfabric and stuff like that. And then we analyze those tries to give you something. Our goal is to be HPC first, so we should be able to scale to 512 node, more 1000, 5000. Our goal is to do full machine and to have low overhead. So we should not, your application should run the same with and without Iprof at first approximation. We don't want to perturbate your application. If you have any bugs, if you find anything, just contact me or Nathan or anyone. Just Slack me. I will be more than happy to talk to you. Tools are meant to be used, and when you use them, you find bugs, and the goal, I think, is to fix bugs. And it is based on a lot of amazing people and tools. So we are based on a lot of open source LTTNG Babel trace too, who are used pretty extensively as a low-level tracer to generate trace points. So it's really nice. Clang to be able to parse header, Perfetto, we'll show some demo and stuff like that. And so Colin, if you remember, 2 days ago maybe, I think it showed you some OpenMP stuff. So I think I want to show you that, what we are doing with that. So the first thing is to be able to just verify or understanding where you are spending time when you are running your code. You know, have this, the first analysis is this kind of summary. So for example, here, Colin was running an OpenMP, and you just do Iprof, the name of your summary, and then you can see where you are spending time in OpenMP. And it can be useful here. It's maybe more, not most of the time, but maybe the number of calls. It's like, oh yeah, how many target regions I have in my code? I should think I have maybe, I do 100 calls and I do 10,000 or stuff like that, right? Or maybe the data transfer. I was thinking I did enter data to be able to minimize the data transfer, but I still see a lot, or what is the issue? So I think this kind of summary are really useful. Maybe something important to say is like the summary are useless if you don't really know your application, right? This summary makes sense because you understand your application, you have expectation, and do they match what really you measure? And in this case, you need to find the bugs. So yeah, as I say here, we can give you summary. This is our first kind of analysis. By default, you just do iprof a.out, you run, and it will give you this summary, this tally, what we are saying. And for example, here, it was an MPI application. And you see here, I do 800 call to MPI barrier, and I do like 2000 call of in the MPI, total MPI. So that means if I count the number of call I did in MPI, I did this number of calls. So I do 2K call. Where if I here, it's on the device, so what run on the GPUs, so the number of kernel, how many time I spend on the GPUs, and I do far less call, 88, but each call take far longer. So that means here I'm good, I'm GPU bound. So I don't care about MPI, MPI is not my problem. So that means I should scale more until MPI is my problem. Or I can start optimizing GPUs, communication, or GPU either communication data transfer or just the main kernel. Talking about data transfer, you see here, we see that 99% of the time in this kernel, so this is a really nice code. That means if I need to do something in this code, I can just optimize the kernel within line 76. If I optimize this kernel, every time would go down, and I will be pretty happy. But you see here also, I do data transfer upon memory copy. And just an overview, right? We have a hierarchy of bandwidth in HPC. So when you go to the network, to the NIC, so when you go from one node to another node, this is the worst. This is super slow. When you go from the CPU to the GPU via PCIe, it's faster. When you stay on the node, it's faster. When you stay inside the GPU to the main memory, it's faster. When you stay in the cache, it's even faster, right? So that means data transfer are slow. You should remove this bottleneck. As usual, question of bottleneck. In theory, MPI may be your bottleneck. You should remove it. Then maybe it's PCIe. Most likely, you should remove it. And just at the end, here you have the compute is the fastest of the fastest. If it is the fastest, you can optimize the fastest. Then a timeline visualization, we can be really nice to see some gap in the timeline and stuff like that. I think EA, for example, when it discussed in this slide the good practice in OpenMP, it shows you a timeline that you can have with a lot of tools. We have also one because I think it's a really nice thing. And you can really see a lot of things. I will spend the next few minutes discussing you the timeline. But yeah, so to do the timeline, you just need to do iprof-l, who is for timeline. And then you will get a file, a Perfetto file, yeah, just that you can just open in this UI, it's a website, and you can open it in Chrome or Firefox, and then you will do this kind of nice things. And you can see, for example, here the OpenMP and the thing like that. If you like visualization, if you want to improve our visualization, I will be more than happy. It's nice. It's always nice to make graph and stuff like that. It's just time consuming to make it look good. So if you think you have a appetite for nice visualization and stuff like that, I will be more than happy to collaborate with you. So some examples that I show when I do some presentation, performance presentation, it is a real code. It's a benchmark, but it shows you what to do. Or what not to do maybe. So this one is the host code. On the top, sorry, my graph should be better. So this one is the host and this one is the GPU. So this one are host call. For example, here the name is short, but it is memcopy. And this one is the time spent on the GPU for the memcopy and for the kernel and stuff like that. So you see here, if you do the timeline, it's pretty bad because you see you are not utilizing the GPU properly. Even if you don't know the kernel or if you don't know this code, you know it's bad because here you have a lot of white gap into your timeline. That means we spend $10,000 to buying whatever an AN100 and you are using it pretty badly, right? Because most of the time you are doing nothing with them. So you modify your code, you remove the gap, you are pretty happy. Maybe you can prefetch some stuff, or maybe you can just do some CPU on another thread, whatever. You are all smart, you can optimize these kind of things. And now you're good, right? No, the code look pretty perfect if you are just a 101 student who is his first time in HPC. So this one look pretty good, right? No gap. Everything is fine. You think you can stop, but you are smarter than that. You have more experience, right? Or just you remember what I said 5 minutes ago that PCI is a data transfer, a bidirectional data transfer protocol. So that means here we are doing two memcopy, and we do a copy in host to device and a copy in device to host. And in fact, this one should be done in parallel. And even better than that, this one is a kernel, this one are data transfer. So all these three things should be done in parallel. The fact that they are not doing a parallel, it's a bug. It's a performance bug, either on your code or on your limitation. So you should fix it. And if you fix it, then this one is a real good timeline that you should see. HPC fundamentally is really about extracting concurrency in your code, right? Your goal as a programmer for HPC system is to understand what can be done in parallel and how you can express that to the runtime so stuff are done in parallel. It is really, if you need to remember one thing from this talk is like you should profile, and when you profile, you should understand if you have enough concurrency, and you should be able to extract the maximum concurrency from your code, right? So for example, from here to here, it's more or less 3x speed up, where a lot of people think this one is the best they can do because no gap on the GPU. Yeah, no, you can always do better. You can have concurrency. Finally, so this one is more like high-level metric, who is useful for, I mean, to get you started, right? Then you can deal far down with map and vtune and stuff like that if you really want to go far more details. But one thing we are doing also is more like low-level driver, and I'm sure you have at least one guy here who is also interested by that. Is like how can you see what is going on at the layers that you are profiling, what kind of argument, what kind of things. And we can do that with Iprof. If you do Iprof-T for trace, it will show you the trace. So it will show you each and every function call you are doing to this API and all the parameter. So for example, here is heap on top of level 0. We have a project to that, and you see, okay, I do a memory field of this size who correspond to the heap, the heap call of this size correspond indeed to the copy of this size. And it can be useful, for example, if you are a 2D memcopy in PyTorch, you have a tensor memcopy or something like that, how it is implemented beyond the hood, if it is indeed calling the low-level CUDA, PTX, whatever, a CUDA call for to do copy region, or if it is maybe just unrolling everything, doing a lot of 1D. So it is this kind of question you want to ask yourself. And this one is really useful for us, the performance engineering who debug runtime. Maybe less for you, but at least this tool allow you to do that. I have 3 more minutes, so I will just, maybe one more high-level visuals, and then I will go to the conclusion is the more you ask, the more overhead you will have, right? There is no such thing as free lunch. So if you ask for a lot of data because you want to have all the call stack, all the CPU scheduling stuff and everything, you will have more overhead because this is a fact of life. You are doing more work, you need to pay the price, right? So this is why if you do the aggregation, it will be faster than if you do the tracing, or the same in any VTune or map, whatever, depending on the option you put. So this one is like, you cannot really complain if it's slow if you add the full profile, for example. For us, we try to do everything locally. So for example, the summary of a summary is a summary. That means we can generate the summary per node during your application, and then we can merge everything. So we scale in O1 compared to the number of host name, right? Not in ON. So this is pretty nice. We are independent of the number of host name for the analysis. So this is why we can scale to a really large system, in theory. In practice, everything is more challenging. So as usual, if you find stuff, just let me know. And right now we do only post-processing. That means we run your application. We try really hard to minimize the overhead for your application. We don't want to perturb your application because we don't want the scheduling to change or to trash the cache and everything. And then we do the post-process, but it takes time. So we have a proof of concept for on-the-fly analysis. Just talk to me if you are interested with that. So in conclusion, modulo THAPI, you will have Iprof, iprof.a.out, you will have the tally, you know where you spend time in which runtime, so you know what to optimize. -T, you have the timeline. Of course, you cannot have a timeline of 10,000 nodes. Too much information, it would be too big, you cannot visualize. But you can do that then in the selected number of rank, and then you can see if you have bubbles, gaps, optimize that. And here it should be iprof dash. This one, sorry, should be L and T. I didn't get my coffee before I make the slide yesterday, so sorry. Here is L for timeline and T, so to have the trait if you already narrow down where it is. For the future work, if you want to collaborate, if you want to work with us, we can improve the timeline visualization. It's the thing we want to do. The processing time, we always want to do some stuff. Add new backend, ITT, Lake Fabric, a lot of Cocos and all of this kind of thing. Cooperate with tracer, for example, with some Python tracer, and how to handle multiple binaries. This one some trivial, just need to put more work. And it's noon, so thank you very much. And please don't hesitate if you have questions, but I understand it's lunch. It has been already a long morning. So I will be there on Slack, or just don't hesitate to contact me. And thank you very much.